raised to the power of 19. And I don't mean just estimating an answer, but finding the exact perfect symbolic solution for centuries, honestly. That's been considered an almost insurmountable challenge in mathematics. Today, we're diving headfirst into a breakthrough that seems to completely redefine what's possible.
That's right. We're talking about Ezouidi's theorem. It's a method that's really shaking up classical algebra. It gives us an entirely new way to approach and, crucially, solve these traditionally challenging high degree polynomial problems with absolute precision.
Okay, so our mission today, unpack the power of Ezoudi's theorem. We want to really get into how it delivers these exact symbolic solutions for polynomials. And then let's compare its, well, revolutionary approach to the older methods, the ones that were less precise. And to really bring it home, we'll dig into a very specific, kind of intimidating example, a degree 19 polynomial. So, okay, let's unpack this a bit more. For centuries, solving these high degree puzzles was like hitting a brick wall. Why was that wall so, well, so unyielding? What made these polynomials such formidable challenges for mathematicians?
Well, traditionally, solving polynomials of degree 5 or higher has been considered immensely difficult, just fundamentally hard. For a very long time, mathematicians had to rely on numerical approximations. Think about classical methods like Newton's method. They're useful, sure, but they inherently risk rounding errors. They simply can't guarantee exact values. You get close, maybe very close, but you don't get the precise answer you might need. And this challenge, it was even codified, formalized back in 1824 with Abel's impossibility theorem. It's really a cornerstone of classical algebra. It states there's no general solution in radicals for polynomials of degree greater than or equal to 5. And when we say radicals, we mean solutions involving things like square roots, cube roots, that sort of thing. So this theorem basically established this long held belief that exact solutions were, well, impossible using those conventional methods for such high degrees. It really set a limit, on what we thought was achievable.
Right. So for nearly 2 centuries, Abel's theorem just stood there like this unbreakable barrier. Mathematicians just accepted that exact solutions for these complex equations were fundamentally out of reach. But then, just last year, 2023, something truly remarkable emerges as Zuidi's theorem. And it claims to, quote, close the door on Abel's assertion. How? How could such a long held mathematical truth be challenged like that?
Well, it directly contradicts Abel's assertion. It does that by demonstrating that even polynomials that would have radical roots, if you could express them that way, can indeed be solved exactly. The genius here, I think, is that Ezouidi's theorem bypasses those traditional radical forms entirely. It just doesn't use them. Instead, it utilizes recursive power sums and complex exponentials to find these precise symbolic roots.
Okay, hold on. Recursive power sums and complex exponentials. Can you break those down a bit? What does that actually mean for someone trying to picture this process?
Yeah, great question. So think of recursive power sums as a meticulously designed sequence of steps, like a recipe. Each calculation builds directly on the previous one, and it systematically transforms the polynomial's terms. It's like a carefully choreographed dance of symbols, really, leading to simplification. And complex exponentials, well, they're a highly elegant and crucially precise way of expressing numbers, numbers that combine both real and imaginary parts. It's just a more sophisticated language for mathematical solutions than simple square roots or cube roots. And when you compare Ezouidi's theorem directly to the classical methods, the differences are pretty stark. Take degree limits. Classical methods just, well, they fail for polynomials of degree 5 or higher. That's Abel's point. But Ezouidi's, it solves any degree, like the degree 19 example we're going to look at, any degree at all. Then think about the form of the root you get. Classical methods give approximations, or maybe radicals if you're lucky enough to be degree 4 or less. Ezouidi's provides exact symbols and these complex exponentials, always exact. And error handling. Classical methods inherently suffer from numerical instability, those rounding errors we talked about. Ezouidi's boasts zero error because it's purely symbolic precision. And finally, generality. Classical methods are often limited, they only work for specific forms. Ezouidi's is universal because of its recursive nature, it applies broadly.
Wow. Okay, so this isn't just a slightly better guess or, a faster numerical method. Not at all. This is about finding the definitive answer, a precise, solvable method. And you're saying it actually outperforms even modern AI techniques because there's no guesswork, no rounding errors. That sounds like a total game changer.
It truly is. And to really grasp this breakthrough, let's consider that polynomial I mentioned, one that would have been an absolute nightmare to solve just, well, a year or so ago. A dense, sprawling equation of degree 19. Imagine x to the 19, x to the 18, all the way down. 19 terms, each with its own specific coefficient.
That sounds like a true mathematical beast, yeah. And how does Ezouidi's theorem even begin to tackle something that intimidating?
Well, this polynomial, px, it has a very specific set of coefficients, the numbers multiplying each power of x. Ezouidi's theorem uses these, they're called L coefficients derived from the polynomial. So you have L0q equals 19, L1q equals 171, and so on. There's a list of them, L0 through L18. Now, here's a crucial nuance. While most of these coefficients are fixed from the polynomial itself, the very last two, L17q and L18q, can actually vary depending on the source or interpretation you're looking at. For instance, in some versions, L17q is 0 and L18q is A31375. In others, L17q might be I, the imaginary unit, and L18q is then A31375 plus I. And for this deep dive, we'll actually consider both interpretations. It really showcases the theorem's flexibility and precision, how it handles these variations.
Okay, here's where it gets really interesting then. How does this theorem actually work its magic? What's the ingenious process behind taking those L coefficients and getting to a solution?
Right. It all starts with expressing the polynomial symbolically using those L coefficients. That's step one. Then step two is the core idea. You calculate a new set of symbolic coefficients. Let's call them SK1Q. And these are derived recursively. There's a specific formula, SK1Q equals sum, CNR, KRNR dash L0Q, K dash R, LR1Q. It looks complicated, but it's a systematic process. This recursive calculation is the key. It lets you work purely with exact symbolic values, completely avoiding any need for numerical approximation. And what's fascinating, truly remarkable for this specific degree 19 polynomial is what happens when you run recursion. Many of these newest coefficients, specifically S0 through S7 and then S9 through S16, they are calculated to be exactly 0. They just vanish through the process. So you're left with only a few significant non-zero coefficients. For example, S8R comes out to be 92377 times 19 to the power of 9. Huge number, but exact. And S17R depends on that L17Q value we talked about. It's either 923751 times 19 to the 18 if L17Q was 0, or 923751 plus I times 19 to the 18 if L17Q was I. Still exact, just different depending on the input.
So this systematic calculation leads to a dramatically simplified form, that original daunting polynomial. The original px could be written as by 19 year r by 18 plus y plus S17rx, thus S17q equals 0y. But because so many of those coefficients turn out to be 0, it simplifies remarkably. It becomes just px s by 18, s8r by 9 plus s17r. Look how much simpler that is.
Hold on, you're saying a 19-degree polynomial, which seemed impossible to solve exactly, effectively collapses into that. X times something simpler equals 0. That's quite a transformation. So one root is immediately obvious then, right? X equals 0.
Exactly. The first root is immediately x equals 0. Simple as that.
Right.
The remaining 18 roots come from solving the part in the parentheses by 18 s8r by 9 plus s17r is 0, 0. Now look closely. This looks like a quadratic equation, doesn't it? But it's quadratic and by 9. It's like by 9, 2s8r by 9 plus s17r is 0, 0. So we can just apply the standard quadratic formula to solve 4 by 9.
Ah, I see. You solve for x to the power of 9 first, using the quadratic formula with those calculated s8r and s17r values.
Precisely. And this step is where those different interpretations of the L17 coefficient feed in, affecting the value of S17R, and thus the solutions for by 9. But the method works perfectly fine for either case. Once you have the values for by 9, taking the ninth roots gives you the final 18 solutions. And these final roots are elegantly expressed using those complex exponentials we discussed earlier, things like e to ki pi 9. This level of precision, getting every single one of the 19 roots exactly, symbolically, is a direct result of the structured recursive steps of Ezouidi's theorem. No guessing, no rounding.
Okay, this sounds genuinely revolutionary for pure mathematics, but maybe for the listener thinking, okay, complex math, but so what? What are the real world implications here? Where does having this absolute precision truly make a difference beyond, the theoretical or the textbook?
That's a really important question. This theorem provides a fundamentally new tool, a new way to solve problems previously deemed unsolvable, or at least only solvable approximately, by conventional methods. The precision that zero error guarantee offered by symbolic solutions is absolutely crucial in many fields. Think about high precision engineering design, advanced physics calculations, perhaps in quantum mechanics or relativity, maybe even complex financial modeling or cryptography, places where even tiny numerical inaccuracies can compound and lead to massive errors or failures down the line. This approach ensures that exact roots can be found for polynomials of any degree, no matter how complex they seem. It just breaks down a barrier that stood for almost 200 years. It opens doors to potentially new levels of accuracy and insight in countless applications where polynomials model complex systems.
It really is a monumental achievement then. Ezouidi's theorem represents a significant leap forward. It proves that even these seemingly intractable high-degree polynomial equations can be solved exactly. It bypasses historical limitations, like Abel's theorem, and it avoids the inherent pitfalls of traditional approximation methods.
Absolutely. And this makes you wonder, doesn't it? It raises an important question, maybe a provocative thought for you listening. What other long-standing mathematical problems currently considered way beyond our grasp, were only solvable approximately? What if they're just waiting for a completely new perspective, a different angle, or maybe another breakthrough theorem like Ezouidi's to reveal their own exact, perhaps elegant solutions? Think about the endless possibilities when we challenge established limitations, not just in math, but really in any field. What else might become solvable?